Yeah. Okay. Okay. The in this session, what we'll be doing is we'll be discussing the SVD. Okay. We'll discuss SVD and then we look at the practice assignment and the activity questions as well as the solve with us also, but only for SVD part. The remaining part, sorry, the remaining part it will be taken by the Vishal sir. Okay, that will be done tomorrow. All right. Okay.
Okay.
So let us begin. How I've started recording. So yeah, we'll be uploading it later. Yes, actually, you can check that channel too. Yeah, everyone, you can just check that channel. There it will be uploaded. Okay, so that's CS2004 channel, right?
No, is it a separate channel or what?
Everything. What?
Is it a separate channel or what?
Yeah, that's a separate channel. That's not the ITM online basic degree channel. It's a separate channel. So in this term, what's happening is that
So
each
so
since we're
so,
like
so
YouTube.
many touch points will create confusion where what is getting uploaded. It will be very tough to track.
True. We agree, but we're trying to solve that. But currently, this is what it is. Like each course has its own YouTube channel, and there you'll be able to find the what do you say uploads whatever license
No,
that happen, right? It will be there. Okay,
sir, I guess officially there is only one channel, IIT Madras, IITM Madras, the BSc, and there
right.
all the videos are getting uploaded.
Yeah, that's previously okay when the sessions were happening on Zoom. That's what used to happen. But right now, all the Gmeet, right? Since the sessions are happening on Gmeet, uh, the the videos are getting uploaded to the like each respective course channel.
Okay, okay,
Okay.
okay.
Yeah. Okay.
So this is a new
So
update. Okay.
yeah. So let us begin. Okay. Let me share 1 second. I'll share my screen and then we'll start.
So tomorrow's session is getting clashed with system command.
Okay. Yeah. See, generally we do not have a session tomorrow. Okay, Wednesday we do not have session since that since the deadline for week 6 is near. That is why we're having the session like that. Okay, we do not have other option there. So
What is DF, sir, for tomorrow? DF.
that's this part the definiteness and all.
Acha, acha, okay, okay.
Okay, yeah. So let us begin. Okay, so we'll be discussing about this singular value decomposition. Okay, that's the main agenda for the session today. Okay, so what we have over here is that see, we know that symmetric matrices can be diagonalizable, right? Symmetric matrices and the Hermitian matrices can be diagonalizable. Okay, so what happens is for those matrices, I mean the symmetric and the Hermitian, we have the eigenvalues as real. Okay, and it is like orthogonally diagonalizable. Orthogonal diagonalizable in the sense like we'll have a matrix, we'll have a orthogonal matrix, okay, Q such that A equals to Q this diagonal matrix multiplied by Q transpose. Okay, so this is what happens for a symmetric or a Hermitian matrix. All right. So here this what happens, but then what about the other matrices? Like in general, when you have this is just an example for this symmetric matrices diagonalization, okay, orthogonal diagonalization, but the every other matrices that cannot be diagonalized, okay. So, but what we can be doing is we can be decomposing it, okay. We can be decomposing it into this SVD form, okay. So, what do we mean by that? Okay, what do you mean by that is that A can be written of the form Q1, Q1 the sigma Q2 transpose. Okay, so this sigma will be a diagonal matrix, but then this Q1 and Q2, just like before here, what do we have here? We have here that this Q. I mean, we just have a singular matrix of Q1 Q transpose, but here it's like these are like two different matrices. Okay, so Q1, and then this Q2 transpose. Each of them are like orthogonal matrices. Okay, but they are not the same. Okay, if they are the same, then it would have been this symmetric matrices. Then that would be the case for this symmetric matrices. Okay, symmetric or Hermitian matrices. Okay, but of course, when you have sufficient Hermitian matrices, if it's complex, instead of having transpose, you'll be having star there. Okay.
Sir, sorry to interrupt. Can I
Yeah.
request something? Sir, can you take a top-down approach because there is some confusion around this? Like, for example, every matrix is diagonalizable or not, or every matrix can be written in the form of SVD. Within that, some of them can be diagonalized because if they're real symmetric matrices or Hermitian, you can diagonalize them with orthogonal matrices. ऐसा एक कुछ tree diagram type कुछ मिलेगा sir? Because there is some
Okay. Got it.
confusion,
Yeah.
as to.
Yeah. Got it.
Thank you, sir.
Okay. So what we have over here is, look at this. We have a matrix. Okay. This will be of two types: real, complex. Okay. In this real matrix, you have your symmetric, non-symmetric. Okay. In the non-symmetric, you have here eigenvalues distinct. Okay. Not all eigenvalues are distinct. Here all eigenvalues are distinct, and in the complex case, you have two types, right? Hermitian, and then like non-Hermitian. Okay. In the Hermitian, okay, we do not have to worry about this, but in the non-Hermitian, eigenvalues same like here before. All eigenvalues distinct. Okay. Non-distinct. Okay, so these are all possible cases we could have. All right. Any other cases that I have left out? No. All right.
Sir, non-symmetric means rectangular matrix, right? Or a separate classification is
No.
needed for
I'm
that.
just talking about this n cross n. Okay. Any one of the n cross n type only I'm talking about. Okay.
Okay.
All this for this. Okay. That we missed. No. Okay. But consider this for n cross n only. Okay. Okay.
Okay.
This is for
May
n
I
cross n.
request something?
Okay.
May I request something?
This is for n cross n matrix. In the n cross n matrix, it could be real complex. Okay. In the n cross n matrix, it could be non-symmetric, symmetric. So square matrix, not the rectangular one. Okay. Okay. So this symmetric matrices, they're like orthogonal diagonalizable, right? Okay. Same for this. Hermitian matrices is also like orthogonal diagonalizable. Okay. All the eigenvalues are distinct. This we have seen. It is diagonalizable. Okay, here we have A equals to PBP inverse. Remember this one? This we have seen. Oh, right. Here, what do we have here? Here we have this A equals to Q lambda, this Q transpose, right? Similarly, what we have is okay. I open two visit. Okay. Here, this will be of the form PBP inverse. Okay, but for the symmetric matrices, what happens? This P inverse is nothing but this Q transpose. Okay, so this will be of the form QA. So not QA. This will write as like something. This form, okay. Q transpose. Okay. This Hermitian matrices, it will be of the same form. A can be A, if A is a Hermitian matrix, then it can be written in this form. U lambda and then this U star. Okay. Star is this U conjugate transpose. Okay. And this can also be diagonalizable. Okay, this can be diagonalizable but not orthogonal diagonalizable. Okay. And this is not diagonalizable. Not diagonalizable. Okay. Clear? So if for it to be diagonalizable, first of all, it should be having distinct eigenvalues. Okay. So and if the distinct eigenvalues, I mean if the distinct eigenvalues, that's why symmetric matches, right? If the matrix is symmetric itself, then it will be like orthogonally diagonalizable. Okay. It will have this form of like, let me rewrite this. It will have this form. Okay. So similarly for Hermitian matrices, these two are like similar. Okay, these two are like similar. So it will have the form A equals to U is lambda U transpose, where U is a unitary matrix. Okay. For unitary matrix, you know the condition U star is equals to I. Okay, just for this orthogonal matrix, we have here Q transpose equals to I, right? Similarly, we have here U star equals to I. Okay, not transpose star. Okay, so this is what it is. This for the diagonalization part. But if you look at the if you look at the SVD, right? Any matrix.
Sir, one trivial doubt, sir. Can you go to previous page?
Okay.
Sir, this when we write, Q transfer equal to I, sir. Hello,
Yeah.
sir. Am I audible?
Yeah. Yeah, you were audible.
So, sir, like sir, this is a condition for orthogonality, right?
Correct.
Q transfer equal to I, right?
Correct.
So whether the reverse is also true, like that they are commutative, like Q transpose Q equal to I, whether both are same or they will be different.
What Q
Like
transpose
writing
Q
Q
equals to I,
transpose.
this you're
Similarly, can
asking?
we write Q transpose Q equal to I? Yes, yes. This one, sir. This one, yes.
Yeah. Q transpose Q is also equals to I.
So both okay.
Yeah, both the same. Here also U star U is equals to I. Okay, you could check that. See, we have here Q transpose equals to I, right? Okay,
So it is
multiplied by Q transpose first. Okay, so
right.
we'll multiply by
Yes.
Q transpose. Okay, and then on the other side we'll be multiplying it by
Okay. Thank you, sir.
what? And then on the other side, this side you can multiply by Q transpose Q. But actually, it is true actually.
Yeah, so the
Um,
other way to do it is if you just take an overall transpose, the inside will
yeah,
anyway flip, and I transpose will anyway be I.
correct. You could do it that way. Yes.
Yes. Going by that logic also, yes.
Okay.
Yes, sir.
So yeah, Q transpose all transpose is it's going to be equals to, yeah. But it's still again going to be equals to this one, right? Q transpose, right? What you're going to get this, right? This is again Q transpose equals to I. But actually Q transpose Q is also equals to I. Okay. If Q is orthogonal matrix, okay, we can do it this way. Okay. This Q transpose equals to I, right? Let us consider Q transpose matrix. Okay. For it to be orthogonal, what's the condition? Q transpose, okay, multiplied by Q transpose whole transpose, it should be equals to I, right? This is the condition, correct?
Yes.
Which will give you what? Q transpose Q is equals to I. This should be true, correct? right?
Yes.
So let us multiply by Q here. Q transpose Q is equals to Q. Okay, and then we'll multiply it by Q transpose now. Q transpose Q transpose is equals to Q into Q transpose, right? But this we know it as like I, right? This is equals to I, this is equals to I, and then we know that this is equals to I. Correct?
Yes.
So
Yes.
basically our assumption is correct.
Okay.
Okay, this is like our assumption is correct.
So basically, it is commutative.
Yeah.
Okay.
Okay.
Thank you, sir.
Yeah. So basically this SVD can be applied for like any matrices. Okay. This decomposition, singular value decomposition, it can be done for any matrices. Okay. Be it real, complex, okay, square, rectangular, symmetric, non-symmetric. Okay. So the only thing is you need to think about this diagonalization part. SVD can be applied for anything. All right. Okay.
Sir, are there any restrictions like it should not be a singular matrix and things like that?
No.
Okay.
There's no restrictions.
This is thank you very much. That was very helpful. One conceptual question. I won't interrupt after this. So,
Okay.
what is the point of diagonalization? I know it's very important, but what is it like exactly? What is the benefit in the long run? If you can just answer that, it may not be now, but during the lecture.
So this actually kind of like that the diagonalized matrix, right? It kind of like represents the represent the actual matrix. That is like that's a benefit of it. So those eigenvalues and then the matrix you get, right, that kind of like those two matrices are like similar actually. So that's the benefit of it. The real benefit of it, it will be actually helpful in like solving this ML problems and all. Okay, which will be seen later. In the algorithms and all, they use this idea to be solving. Okay, the exact real part you will not be able to see clearly here. Okay, but in the future courses, yes. And then when you're trying to learn about the algorithms, ML algorithms, then you'll be able to see it. Okay. Yeah. So this they just check this. Okay. They diagonalized and then they have said that this Q and then Q transpose. Okay, this Q transpose equals to I. Here itself you could check that Q whether Q transpose Q is equals to I or not. Okay. Yeah. So as we have said here, for singular value decomposition, it can be applied. It can be applied for like any matrices, any matrix. Okay, but how do you get this? A equals to this Q1 sigma Q2 transpose. Okay, since A is of like M cross N, we'll be generalizing it. Okay, we'll assume it to be a rectangular matrix. Since like square matrix is also kind of like a rectangular matrix where N equals to M. Okay, so this Q1 will be of the form M cross M, and then this Q2 transpose will be of this form N cross N. Okay. Now we have this. Okay. Now we have this sigma, right? Okay. So this Q1 and Q2, they are like orthogonal, but they are not equal. Okay. If they are equal, then A should be this symmetric matrix. Okay. So we check for like this sigma it can have the zeros also in the diagonal elements. Okay, but whatever the other elements we have, non-zero elements in the diagonal, like in the diagonal, they should be greater than zero. Okay, this will be like exactly proving in a bit. Okay, so sorry. Okay, now we have here a equals to M cross N. Okay, A transpose A, it's going to be symmetric and real. Okay, so how do you check how do you check whether A transpose A is symmetric or not? A transpose should be equals to A, right? Like if A transpose equals to A, then it's symmetric. Correct? So for A transpose A, okay, for A transpose A, it should be equals to what? A transpose A whole transpose, correct? If this is true, then we can say that A transpose A is symmetric. So we check this. This will be equals to A transpose multiplied by A transpose whole transpose, okay, which is nothing but A transpose A. This is equals to this. So basically A transpose A is symmetric, okay. This entire matrix A transpose A, you could consider this as X, okay. Since X equals to X transpose, this X is symmetric, which basically says A transpose A is symmetric, okay. Clear that one? Okay. Is that clear? Okay, hope that's clear. So A transpose is symmetric and real. Okay. So we have here there exists a base of orthonormal vectors, right? Since it's like symmetric matrices, okay, we can be getting this orthonormal vectors x1 to xn corresponding to the eigenvalues lambda 1 to lambda n. Okay, whatever lambda whatever eigenvalues we have corresponding to that, we can be getting the orthonormal vectors. Okay, we know that for a distinct eigenvalues, okay, the corresponding vectors, right, the eigenvectors, they'll be like orthogonal to each other. Okay, we can get the we can take the length of the vector as 1, and then we can form this orthogonal vectors. Okay, so since this lambda 1 and then this x1, right, they belongs to this A transpose A, we can write this as like A transpose A xi equals to lambda xi. Okay, then then what we can say is, okay, by doing this A transpose A xi dot xi, okay, we can get this as like lambda A xi dot xi, since A transpose A xi equals lambda A xi. Okay, but xi dot xi is equals to 1 because it is orthonormal, right? Orthonormal vector means that the length is equals to 1. So the length of the norm of xi, right, that is equals to 1. Okay, but A transpose xi dot xi, okay, if we do it this way, the dot product of these two, it's nothing but the transpose, right? A transpose xi transpose multiplied by xi, which gives you xi multiplied by A transpose xi. Okay, and this can be written as AXI transpose. This xi transpose A transpose, it can be written as AXI whole transpose, because AB whole transpose equals to B transpose into A transpose. Okay, so using that, AXI transpose multiplied by AXI is nothing but norm, right? I mean, what is the length of a vector? Length of a vector is nothing but X transpose X, right? So similarly, AXI transpose AXI is nothing but the length of AXI whole square. Okay, which basically says lambda is equals to the norm. Okay, the lambda is equals to norm whole square, and the length will never be negative. So basically, the length of the eigenvalue, so basically the value of the eigenvalue will always be, it will never be negative. Okay, it will always be positive or 0. Okay, so we'll be like ordering the eigenvalues. Okay, so this is not exactly required, but then this how we form this SVD. Okay, that is just norm we follow. Okay, but you'll order this eigenvalues in their like increasing order or like decreasing order. Okay, so generally we do it in the decreasing order. Right. So since we have this of like n cross n, right, we have this of like n cross n, right, what can happen is it need not be of like that much, the eigenvalues we may not be getting as much as the length of it. Okay, so we can be having non-zero eigenvalues, and then the remaining eigenvalues can be equal 0. Okay, so sigma is all called singular values which are like not equal to 0, and then like positive. Okay, so all this lambda 1 to lambda r, they are called as the singular values. Okay, the square root of it. Okay, sigma is equal to square root of lambda a. This sigma is the singular value. Okay, singular values for that particular matrix A itself. Okay, correct. Okay, so basically the singular value of a matrix is nothing but the square root of the eigenvalue of A transpose A. Okay, all right. Now let us look at the reason why we are doing this. Y equals to 1 by sigma AXI will be coming to know in a bit. Okay, because this actually helps us to form this Q1 and Q2. Okay.
Sir, one quick question, sir.
Yeah.
Just clarifying.
Huh.
So when you see, there is difference between orthogonal vectors and orthonormal vectors, because orthonormal, the norm is 1. But when we say orthogonal matrix, it means orthonormal vectors only, right? There's no difference between orthogonal matrix and orthonormal matrix.
Okay. See, the difference is in the vectors you're talking about. Okay. Whenever you have the orthogonal matrix, it contains orthonormal vectors.
Yeah, that's what I'm clarifying.
Yeah,
Because
yeah. But
when you say orthogonal vectors in isolation, not in matrix form, but in isolation, then orthogonal vectors and orthonormal vectors are different.
correct.
Whereas here, orthogonal matrix will have orthonormal vectors. So
Correct.
that is a little confusing. I
Yeah.
just wanted to double check. Got it.
Yeah.
Thank you.
The thing is, for orthogonal vectors, the length need not be equals to 1. But for orthonormal, it should be equals to 1.
Correct.
Okay.
But in case of matrix, orthogonal matrix or orthonormal matrix is the same thing actually, because it has orthonormal
Yeah.
vectors.
That is why we do not explicitly mention the name called orthonormal matrix. Okay? Because
Correct.
both are same.
Correct. Thank you.
Yeah. Okay. So let's consider this vectors. Okay, ya equals to 1 by sigma axa. Okay. Now if you look at this, the norm of axa, right, that is equal to square root of lambda a, because if you check here, okay, lambda is equals to the norm of the axa whole square. So basically the norm of the length same. So basically axa is equals to square root lambda I, and then sigma I is also equals to square root lambda I. Okay, you have defined this. So basically the length of this vector is equals to 1. So all these vectors are like unit length. Okay, and then for distinct for distinct vectors, ya dot yj, axa dot axa, it will be equals to 0, because xi and xj, they are like perpendicular to each other. Okay, so this is just a basic proof for that. So here what we have is we have the vectors. Okay, so here this y1 to yr only will be having, because only until then we have this non-zero eigenvalues, right? The remaining eigenvalues, they are like 0. So basically you'll be getting only y1 to yr, but we can extend it in the sense like, let's say like you need to have three vectors. Okay, you need to have three orthonormal vectors, but you found only one. Okay, you can get the other vector which is like perpendicular to these two vectors. Okay, so by extending it to, we can extend it to m. Okay, so we can extend it to m. So this y1 to yr, will be extending it to m. So basically we'll have a orthonormal vectors of size of this m. Okay, so so now this q1 will be equals to y1 to ym, and then this q2 will be equals to x1 to xn. Okay, then okay, yeah, now this sigma, right, what we have is, for this SVD, we have here a equals to q1 sigma q2 transpose. This is the one, right? Yeah, q1 sigma q2 transpose. Now if you could just prove that, multiply this by q1 transpose A will be equals to q1 transpose q1 q2 transpose. Okay, and this is equals to I. Okay, later this q1 transpose A will multiplied by q2 is equals to, this one equals to I, so I'm not writing it, sigma q2 transpose q2. Okay, and then this q2 transpose q2 is equals to I, because q2 is an orthogonal matrix, and here also q1 is also orthogonal matrix. So basically, if you could prove that q1 transpose A q2 is equal to sigma, okay, this diagonal matrix, okay, then we were able to prove that, we can write any matrix of this form. Okay, we can decompose any matrix into this into this SVD form. Okay, okay, we have here this q1 transpose A q2, right? Okay, so A q2 is what? q2 is this x1 to xn, right? So this will be equals to a q2 will be equals to ax1 to axn. Okay, AX1 to AXN. Okay, now we will be looking at this sigma ij. If you look at this, right, the matrix that we found is this will be of the form M cross. Wait. What we have is we have here y1, y2, yeah, y1, y2, y3, y4, and so on, ym, right? So these are the vectors. Since we have done the transpose of it, we are writing it this way, okay? And this will be multiplied by ax1, ax2, and so on, axn, correct? Now what will be the let's say like resultant matrix? This will be, let's call it R, okay? What will be the Rij element? Okay, Rij element, Rij, right? If you want to get Rij, you should be taking it the yi, okay? Ya should be multiplied by axj, right? Correct? See this y1 multiplied by ax1, it will give you r11. R11 is equals to y1 multiplied by ax1. Similarly, R12 will be equals to y1 multiplied by ax2. Correct? Right? This multiplied by this multiplied by this, it will give you the R12, right? And then you'll be doing it R13. Correct? This is how you do it in a matrix multiplication, right?
Yes, sir.
Similarly, Rij will be equals to yi multiplied by axj. Okay? But then what is this yi? Okay, multiplied by the sense like dot product, okay? This since it's for like vectors. Ya dot axj. We have this ya is equals to what? 1 by sigma I into axj, right? Okay, correct? Right, this ya I can derive it as like 1 by sigma I into axj, right? So axi dot axj, this will be equals to what? This will be equals to 0 if I not equals to j, because we have seen this axi dot axj, okay? Here we have seen this. This will be equal to 0. All right. So axi dot axj, this will be equal to 0 if I not equal to j, okay? If I is equals to if I equals to j, then what does that say? Say axi dot axi, right? So this is nothing but norm of axi whole square, and then this is axi whole square is nothing but lambda 1, right? Now norm of axi whole square is nothing but lambda 1, and the sigma is equal to square root lambda 1, which will basically give you square root lambda 1, okay? And this is the matrix sigma we are talking about, okay? So basically the sigma matrix is equal to this d0 0 0, right? This will be equal to 0 when I not equal to j, okay? And then this d will contain this value of like square root lambda 1, square root lambda 2, square root lambda 3, and so on, square root lambda r, okay? And then the remaining eigenvalues, they are like 0. That is why we have this 0 here, okay? So it's not like all the diagonal values are not are non-zero, okay? They can be equal to 0 also, okay? But definitely they won't be negative, okay? Is this clear, the SVD, how we arrived at this?
Sir, this sigma matrix will be M cross N or square matrix?
The sigma matrix,
This R matrix, sorry, R matrix. We have written R equal to this the row wise times the matrix AXJs, right?
this will be equal to m cross n.
Ah,
This will be equal to m cross n only, because see, for it to be multiplied with this, right, for sigma to be what do we have here? We have here A equals to Q1 sigma multiplied by
Yes.
Q2 transpose, right?
Yes.
Correct. And then this Q1 is what? M cross M, right? Q2 transpose is what? N cross N, right? So definitely the sigma should be M cross N. So only when it's of M cross N, this can be multiplied with this. And then only if it is of this M cross N, this can be multiplied
Okay.
with
So
Q1.
if sigma
Okay.
is M cross N, then how come it's a diagonal matrix? Because only square matrix are supposed to be diagonal matrix, right?
Right. Yeah. So what we have there is let's say like we have here whatever positions we have like RIA, right? Okay. Those elements it will be having this square root lambda I. Okay. The remaining elements it will not be what is it? It will be equal 0 for the sigma.
Okay.
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 So let's consider like 3 cross 4. Okay. So it will have what R11. Okay, let's just write the sigma. Okay. Sigma 11, sigma 12, sigma 13, and then sigma 14, right? Sigma 12, sigma 22, sigma 23, and sigma 24. Sigma 21. Okay, and then 31, 32, 33, and then this 34. Okay. Let's say like here we have like two non-zero eigenvalues for A transpose A. Okay, two non-zero eigenvalues. So basically, we'll have square root lambda 1 and then square root lambda 2. Okay, so here this will be like, so this matrix will be equals to square root lambda 1 0 0 0. So this will be equal 0 square root lambda 2 0 0 and then 0 0
Okay.
0
Okay.
0.
So it's not a diagonal matrix exactly, right?
Yeah.
Okay. Okay. Thank you, sir.
Okay. Okay. So that's what we have here for this. So okay, so the sigma equals to Q1 transpose A Q2. That's like proved. Okay, then okay. So here we can say this sigma is not a diagonal matrix. Okay, but then you could see here this D, right? D is R cross or diagonal matrix, and then remaining 0 0 you could be having. Okay,
So that D is diagonal, right? Matrix.
this D is diagonal. Okay,
Okay.
the remaining not diagonal. Yeah.
Okay. Right. Thank you, sir.
Here too, you could think of it like this as the diagonal part, and then the remaining this one as 0 0 zeros. Okay.
Okay, sir.
Okay. So if you could, we have here A equals to Q1 sigma Q2 transpose, right? If you multiply it by A transpose, which is basically like if you transpose this and then like multiply with each other, let's just do that. A equals to Q1 sigma Q2 transpose. If you do this A transpose is equals to Q1 sigma Q2 transpose, full transpose, right? Okay. This what we'll do is this Q1 sigma will consider as A, this will consider as B. Okay. All right. So this is of the form AB transpose. AB transpose is nothing but sorry Q2 transpose whole transpose multiplied by which is nothing but B transpose. Okay. Multiplied by A transpose, right? Q1 sigma transpose. Okay. Sorry. Now this is of the form AB. Now we'll do it again. Now this Q2 transpose whole transpose is nothing but Q2. This we could write it as B transpose A transpose, which will give you sigma transpose multiplied by Q1 transpose. Okay. Now this A transpose is equal to this one. If you do this AA transpose, okay, AA transpose is equal to Q1 sigma Q2 transpose multiplied by Q2 sigma transpose Q1 transpose. Okay. Q2 transpose multiplied by Q2 it's equals to I. because Q2 is orthogonal. Okay, which will give you Q1 sigma transpose Q1 transpose. Okay, the sigma transpose, it will again be equal to this diagonal matrix. Okay, sigma transpose, why it will be equal to diagonal matrix, I'll tell you. Sigma is what? M cross n. Sigma transpose will be what? N cross M, right?
So sigma
So,
transpose is M cross N.
yes, M cross M. So now this is a diagonal matrix. Okay. Now, which basically is of the form like Q1, okay, Q D, some diagonal matrix multiplied by Q1 transpose. Okay. If this is of the form, what does this say about this matrix? A transpose is symmetric, right? Which we already know.
Yes.
Okay. Now, basically, the diagonal also which also says that this Q is what Q contains this Q1. Okay, Q1 contains the eigenvectors, right? We know that for a symmetric matrix, we'll write this as like A equals to Q this lambda Q transpose, right? Where this Q contains the eigenvectors of A, right? Correct?
Yes, sir.
Eigenvectors of A, right? Which basically implies here that Q1 contains the eigenvalues of A transpose. Okay, the eigenvectors of A transpose goes into Q1. So similarly, we could do that for A transpose A. Okay, the eigenvectors of A transpose A go into Q2. All right. Yeah. So that's I mean that's a basic intro to this SVD part. Now, if you could look at this example. So here in this example, we just what we'll be doing is given A, we look at this A transpose A. Okay, we look at the A transpose A. We look at those eigenvalues. Is a matrix A diagonalizable because the eigenvalue of A is root 2, right? Since eigenvalues of A is root 2, it's repeated, right? What did I tell you? A can be wait, sorry. A can be diagonalizable when all the eigenvalues are distinct, right? Here if the all eigenvalues are not distinct, then it's not diagonalizable. So yeah. In this particular case, since the eigenvalues are like same, the root 2, okay, the basically the matrix is like not diagonalizable. All right. So then what do we have? We have here, we can look at this. So 1 0 is eigenvector, and there aren't any more linearly independent eigenvectors. Yeah, obviously because we have only one eigenvalue. Then for us to do this, for us to do the SVD decomposition for the same matrix, root 2 1 0 root 2, what we need to do is we need to find the eigenvalues and then the eigenvectors of A transpose A. Okay, using that we can find the y1 and then the x1 too. Okay, y1 matrix, x1 matrix, we can get the eigenvalues of A transpose A, right? It will give you, based on that you can find this root lambda 1 root lambda 2. Okay, so by doing this A transpose A, we got this 2 root 2 and then root 2 3. Okay, for this A transpose A, we got the lambda 1 lambda 2, which basically will give you this singular values. Okay, root lambda 1 root lambda 2. We got the sigma 2001. Okay, since this is of the form this M cross, here this is square matrix, right? So because of that, the sigma also will be a square matrix, and then this sigma 1 sigma 2 will be going in the diagonal elements. Then what we can do is we can find this we can find the eigenvectors of A transpose A. Okay, and then we know that we know that the eigenvectors of A transpose A will go into Q2, right? The eigenvectors of A transpose A will go into Q2. So based on that, we got here x1 equals to the first eigenvector corresponding to the 4. We can get as 1 root 2 and then this root 2 minus 1. We know how to find the eigenvectors based on the matrix and then the eigenvalue, right? So then we can use this x1 x2, and based on x1 x2 we can get the y1. Okay, because we know sigma 1 y1 equals to x1 and sigma 2 y2 equals to x2. Okay, we can multiply a with x1. Okay, not this a transpose a with x1. So ax1 and then ax2, based on that we can get this y1 y2. Okay, once we got this y1 y2, we can get the q1. So since we have this q1 q2 and then the sigma, we can check for this. Okay, which we are not going to do, but yeah, actually this basically says that we can be doing it for any matrix. Okay, like we did not like we did not like take a particular matrix for the SVD. We have just done that for like any matrix. Okay, yeah, so that's the basics. Okay. Now we can look at this activity questions. Okay, every matrix can be diagonalized. No, that's not correct, so that's false. Any questions until now? Yeah, any questions until now?
No, sir. But derivation is bit involved.
What? Derivation is
Proof is,
different, yes, sir.
proof is bit involved.
Okay.
I have a question here. If every matrix is not diagonalizable,
Correct.
then how do we actually go and solve it? Sorry, if you had covered that earlier, I'm sorry I missed that. But if we cannot diagonalize the matrix, then is there any alternate approach to it, or?
No,
That is the SVD approach, right?
yeah. So we
Okay.
will not be able to diagonalize it. We'll be able to decompose it into this SVD form.
Okay. Okay.
Yeah. So every real matrix can be factored using SVD. That's true. Okay. So when we have here, if M cross n matrix A is decomposed, A equals to Q1 sigma Q2 transpose, where Q1 and Q2 are orthogonal. Sigma is a diagonal matrix. The dimensions of Q1, Q2 are okay. That's kind of straightforward. Q1 will be equals to M cross M, and then this Q2 should be equals to N cross N. Okay, and then the sigma should be equals to M cross N. Okay. Yeah, this fourth one will be correct. Okay. The singular values of matrix A are the eigenvalues of A transpose A. Okay. Square root of eigenvalues of A transpose A.
So what is this one, sir? Can we discuss more?
This one?
Yes.
Okay, this one we already checked it here. This one it's already done there in the here we have this A transpose A, right? This lambda I. Okay. This lambda I, whatever you're having, they are just the eigenvalues of A transpose A, right? So yeah. The values which go into the sigma, they are nothing but the square root of the eigenvalues of A transpose A. Okay. Singular values of the eigenvalues, yeah. Okay. Actually, I guess the square root of the eigenvalues of A transpose A and then A transpose, they both should be same, I suppose. Okay. Check on this. First, definitely it should be the square root of eigenvalues of A transpose A. Whether it's going to be this opposite. Okay, let's check on that. Okay. A equals to Q1 sigma Q2 transpose, and A transpose will be equals to. Okay. This we have checked A transpose, right? It's going to give you Q2. Okay. Okay. So what we can check is we can check that square root of eigenvalues of A transpose is same as the square root of eigenvalues of A transpose A, because we could check before that. Right. So here this sigma transpose, right? Sigma transpose, it contains the eigenvalues of AA transpose, right? Because of it is of the form Q1D Q1 transpose, correct? For AA transpose. Similarly, if you look at A transpose A, okay, A transpose A, what you'll be getting is you'll be getting Q2 sigma transpose Q E sigma transpose sigma into Q2. Okay, this is what you'll be getting. And then since sigma is equal to D000, right? Okay, sigma transpose will be equal to sigma. Okay, now. Yeah, actually, it won't be equal because let's say okay, let me show you this. We have here sigma transpose, right? Sigma is a form m cross n, right? Okay, and then sigma transpose is of the form n cross m. Okay, so sigma transpose, it will give you m cross m. Okay, correct? Yeah. So, but if you look at this, right, this is nothing but D000. Okay, so these are the form R cross R, right? Multiplied by this transpose one. Here in this transpose one, this is going to be the same, and then these two are going to get exchanged. Okay, these two are going to get exchanged. So when you multiply these two, basically you're just multiplying the same one. The same thing is going to happen if you do this one, sigma transpose sigma. Okay, sigma transpose will be of the form n cross m, sigma will be of the form m cross n. This is going to give you n cross n matrix. Okay, even though it is giving n cross n matrix, okay, whatever non-zero values you have, okay, whatever non-zero values you have, that will be of the form lambda 1, lambda 2, and so on, lambda r only. Okay, see, the same thing is going to happen here for this lambda 1, lambda 2, and so on, lambda r, and then the remaining values will be equal to 0 here. Here the remaining values will be equal to 0. Here this will be of the form n cross n. This will be of the form m cross m. Okay, so yeah, actually the eigenvalues of A transpose A and the AA transpose both are going to be the same. Okay, that is why the singular values of matrix A or either the square root of eigenvalues of A transpose or square root of eigenvalues of A transpose A, both are same. You can actually check this. You can check this. Okay, for example, let's take like sigma is equals to. Are you following me on this? Hello. No.
Honestly, it's a little fast.
Okay. Okay. So basically, what I'm trying to say is that see this A transpose equals to Q1 sigma transpose Q1 transpose, right? Okay. So the eigenvectors of A transpose goes into Q1, correct? And which basically means sigma transpose. If you multiply these two, the resultant matrix it should contain the eigenvalues of A transpose, right? Am I correct on this? Sigma transpose, it should give
Yeah.
you the eigenvalues of A transpose because for a symmetric matrix A equals to Q lambda Q transpose, this lambda it contains the eigenvalues of A. Eigenvalues of A, right? Which basically says sigma transpose, whatever diagonal matrix resultant we have, that should contain the eigenvalues of A transpose, correct? Is that clear? No?
Yes, it is.
Right? Okay, so similarly, if you look at A transpose A, it should contain A transpose A, the diagonal values for this, the eigenvalues, it should be there in the sigma transpose sigma, correct?
Right.
So now if you look at it, sigma, let it be equals to R1, R2, R3 and so on, Rn. Okay, remaining are 0, 0, 0, 0. Okay, sigma transpose, it will be equals to R1, R2 and so on, Rn. These are not going to change. Okay, these are not going to change. It's going to be 0, 0, 0 multiplied by same one. The diagonal positions are not going to change. Rn. Okay, multiplied by 0, 0. Okay. Here the dimensions are going to change. Like this of the form m cross n. This is going to be the form n cross m. Okay.
Yep.
Okay. Which will basically give you R1 square, R2 square, R3 square, and so on. Rn square. 0. Okay. 0, 0, 0. Am I correct on this?
Yep.
These are the form m cross m.
Mm-hmm.
Similarly, if you do for sigma transpose sigma, so here which basically means the eigenvalues of this sigma transpose, it gives you what? AA transpose, right?
Yeah.
AA transpose, yeah. So basically the AA transpose eigenvalues are R1 square, R2 square, and so on, R square. Okay, it should be R. Okay, both have a star. Sorry. Okay, maybe let's call it like RP. Okay. Okay. P singular values we have. Okay. So basically R1 to RP square, we have the eigenvalues. Okay. These are the eigenvalues of A transpose. Now if you look at sigma transpose sigma, which is again going to give you R1 to RP values 0, 0, 0. But these are the form n cross m. Similarly, sigma we have seen R1 to RP 0, 0. But these are the form m cross n. The resultant matrix will be R1 square, R2 square, and so on, RP square 0 from n cross n. Okay. So basically, sigma transpose sigma, this is nothing but this gives you the eigenvalues of A transpose A, right? So basically, these eigenvalues are R1 square, R2 square, R3 square, and so on, RP square, which are the same as for A transpose. Okay. Clear?
Yeah.
Okay. So now it's clear that the
So
eigenvalue
it doesn't matter
A
which
transpose-
way I multiply, is it?
Yeah.
Is that the conclusion? Okay.
Can I repeat?
So it doesn't matter which way I multiply, sigma transpose sigma or sigma into sigma transpose. It's going to be the same.
No,
The
the
eigenvalues.
the non-zero values are going to be same.
Yeah.
The dimension is going to change.
Yeah. Okay.
Others are able to follow. So I'm able to hear only one response. Okay. You can just cross-check this also if you want. You can just take some dummy sigma and then like check for the sigma transpose or sigma transpose sigma. Okay.
One question I want to ask here. Okay, we know this property now. Is there any benefit of knowing this property? Is it something which we can use? Because dimension is changing. That means I can't apply it whichever way it is. It has to be either A transpose A or A into A transpose. So the order change, how does it benefit me? Okay, that's something which I'm trying to understand.
No, the order change. The only reason I have showed that is
Mm.
just to show that for this example, right?
Mm,
You
mm.
might be seeing that the lambda one is nothing but the square root of eigenvalues of A transpose A. I just
Right.
want to show that even for the eigenvalues of A transpose, they both are same. So
Okay.
these two are like same. Just for this question, I have just showed that.
Okay.
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 So
Okay.
for you
Alright.
for you to solve that problem, right?
Mhm.
You could it's better to follow just even while solving problem, you could use this like but that's going to be a bit tricky because if you know two ways to solve it, right? You could mix it up.
You get confused.
Yeah, you could mix it up. So generally, what here Sarah shown is
A
find the
transpose A.
eigenvalues and eigenvectors of A transpose A,
Mhm.
and for using that we find this x1 x2, okay,
Mhm.
and then that using that x1 x2, using the relation that y1 is equals to ax1, we found it, right?
Mhm.
Right. And then
Mhm.
the okay, so the other way could be that you can find this for A transpose you could do, okay, for A transpose you could find the eigenvalues which will be the same anyway, but then based on the A transpose, right, A
Mhm.
transpose, you can find the eigenvectors. Those eigenvectors will be for y1 y1 to yn, okay,
Mhm.
y1 to ym, sorry. So y1 to ym you'll be having, and using those y1 to ym you can be finding this x1 x2 and so on, this xn. Those
Okay.
you can be
Okay.
finding, but that will be like mix up. Let's just
Okay.
follow
Okay.
once. I mean one way. Okay.
No worries. No worries. Thank you.
Yeah. Okay. A equals to q1 sigma q2 transpose. Then A transpose is for A transpose. A transpose it will be equals to q1. It should be equals to q1 sigma
Sigma
transpose.
transpose Q. Q transpose. Sorry.
Yeah.
Mm.
So similarly for A transpose it will be the opposite of it. Q2 sigma transpose sigma Q2 transpose. Okay.
Yeah.
Here you could think of it like these two are same. Option number B and C are same, but then the dimensions of sigma transpose are not same as the dimensions of sigma transpose sigma. Okay. That's the only difference there. Okay.
Just 1 second. A transpose into A is leading to Q2 sigma trans. Why is the transpose going to the other side on for the Q?
Here this one.
Yeah, yeah. When
This,
we multiply,
it should always be there, right? Because A equals to, I mean, a symmetric matrix will be equals to
Q
Q lambda Q transpose, right?
Q transpose. Okay, transpose. Sorry. Yeah, yeah, yeah.
Which of the following statements about matrix decomposition is that true? Matrix decomposition is yeah, okay. Eigenvalue decomposition exists for only real symmetric matrices. No, that's not true. Okay, it can exist for it can exist for the not normal matrices also. Any matrix can be factored into single value decomposition. That's correct. Okay. The eigen decomposition, the orthogonal, the ortho. This is eigen decomposition. Okay, it can be existing for this non real symmetric matrix also. So option one is not correct. Any M cross N matrix A can be written as Q1 sigma Q2 transpose. And the dimensions are Q1 Q2. Okay, it's same question just repeated at the top. You will form M cross M and then M cross N. For any real M cross N matrix, A transpose is it will be real and symmetric. Okay. Any M cross N matrix A can be written of this form. Eigenvectors of A transpose go into Q1. Eigenvectors of the first one is correct. Eigenvectors of A transpose A go into Q2. That's correct. Yeah, 1 and 4. Okay. Okay. This because we didn't check this. Only 2. Okay. You look at the second one. Which of the following matrices are similar to 1, 2, 2, 3? Okay. Similar matrices. Similar matrices is nothing but two matrices. Okay. A comma B are similar. Okay. A comma B are similar if A equals to something like P inverse. Okay. This P can be any matrix. P is like any matrix. I mean, any matrix in sense such like not like any matrix. There exists a matrix P such that you read this. P is like some matrix. Okay. Okay. For some matrix P, if we have this form of like P equal A equals to PB P inverse, then we can say that A comma B are similar. Okay. Based on this, we suppose let's say A is symmetric. Okay. We have here Q A equals to Q lambda Q transpose, right? Q transpose is nothing but the Q inverse. Okay. So basically, this diagonal matrix of A, okay, and then the A, they are similar. All right. So for this particular one, 1, 2, 2, 3, basically we need to find the eigenvalues of A. That will give the similar matrix. Okay, so we have here what 1, 2, 2, 3. Lambda minus 1 into lambda minus 3. I'm trying to find the eigenvalues. Minus lambda and minus lambda. Determinant is 0, which basically gives you lambda square minus 4 lambda plus 3 minus 4 is equal to 0. Lambda square minus 4 lambda minus 1 is equal to 0. Lambda is equals to minus b plus or minus square root of b square minus 4ac by 2a, right? Minus b is 4 plus or minus square root of b square is 4 square, 16 minus 4ac, 4 into 1 into minus 1 divided by 2a, a is equals to 1 here. Okay. Which basically will give you 16 minus 4 is 12, right? Four plus or minus
2 plus or minus root 3.
2 root 3 divided by 2, which will basically give you 2 plus or minus root 3. Okay. Oh,
So it will be root 5, sir. It will be root 5. It is minus 4 into minus 1 plus
okay,
4.
okay,
Sir.
okay, sorry, yeah, correct. 16 plus 4, 20, yeah, 2 root 5, okay. So the similar matrix for this is 2 plus root 5, 2 minus root 5, yeah, that's correct. Or what do we have? This could also be there. Okay. This, no, only this one, yeah. SVD of 2, 2 minus 1, 1. 2, 2 minus 1, 1. Okay. What we'll do, we'll do this A transpose A. Okay. A transpose A is nothing but, first we'll do A transpose. A transpose is equals to 2, 2 minus 1, 1. Right? So A transpose A is 2 minus 1, 2, 1 multiplied by 2, 2 minus 1, 1. Which is equals to 2 square plus 1, 5. 2 minus 1, 2 into 2, 4. 4 minus 1, 3. 2 square minus 1, again 3. And then 2 square plus 1 square, 5. Okay. So for this lambda values will be equals lambda equals to, we need to find the eigenvalues for this. 5 minus lambda into 5 minus lambda, lambda square minus 10 lambda plus 25 minus 9 is equal to 0, which implies you are following me, right?
I think 2 and 8, sir. Lambda value will be 2 and 8.
Okay, but that's okay. You are able to follow me, right? whatever I was trying to say.
I think you are following those steps what professor had written, like right step one, step two, and all these things.
I'm sorry, can you repeat?
In order to find out SVD value, you are just replicating those steps as professor had shared.
Yeah, yeah,
Like
yeah,
step
yeah,
one,
yeah.
step two, right? Yes.
Correct.
Yes. So I think lambda will be 8 and 2 here, sir.
Plus 17 or 16. Okay.
16, 16.
Okay, yeah, 2 and 8. Okay.
Yes, 2 and 8. Yes.
Lambda is equals to 2 and 8. Okay. Now we have what A transpose A minus 2i multiplied by x1, it should be equal to 0, right? Similarly, A transpose A minus 8i multiplied by x2, it should be equal to 0. Okay. Now let's do this. A transpose A is equals to 5335 minus 2i, right? It should basically give you 3, 3, 3, 3 multiplied by this xi x1 value. I'll write it as like x11 and then this x12 is equal to 0. Okay. Let us consider this as 1. So this will be equal to minus 1, right?
Yes.
Okay. Now this is like the first eigenvector is 1 minus 1. If you normalize it, you'll get it as 1 by root 2 minus 1 by root 2. Okay. That is for the first one. If you look at the second one, that is what 8, right? 8 is going to be minus 5, okay? I mean 5 minus 8, it's going to give you minus 3. It's going to be minus 3, 3, 3, 3. Okay. Now x22 should be equal to 0. You consider this as 1, this will be equals to minus 1. Sorry. If you consider this as 1, this will also be equals to 1. Because 3x21 minus 3x1 plus 3x22 it should be equal to 0. x21 plus x22 should be equal to 0. So second vector x2 is equals to 1, 1, 1. If you normalize it, it will give you 1 by root 2, 1 by root 2. Okay. What we need to find out is, we know that x1 and x2 are like perpendicular to each other. Right? If one vector is 1 by root 2 minus 1 by root 2, the other one should be 1 by root 2. Okay? Others, please mute yourself. Please mute yourself. Okay. Okay, so we have here x1, x2 we have. So it will basically give you q2, right? q2 is equals to this one, x1, x2, 1 by root 2, 1 by root 2 minus 1 by root 2. And then q2, sorry, x2, 1 by root 2, 1 by root 2. Okay, this is going to give you q2. In order to find q1, we need to find y1 equals to ax1. Okay, so a is equals to 2, 2 minus 1, 1. Okay, so this do we have here 2, 2 minus 1, 1. So ax1 will be equals to 2, 2 minus 1, 1 multiplied by 1 by root 2 minus 1 by root 2. So this is going to be equals to 0. And this will be minus 1 by root 2 minus 1 by root 2 minus 2 by root 2 minus root 2. Okay. So this is going to be equal to 0. My matrix A is correct, right? 2, 2 minus 1, 1. 2, 2 minus 1, 1. Yeah. Okay. Yes. Y1 is this one, and then Y2 is AX2, which is nothing but this multiplied by 1 by root 2, 1 by root 2. This is going to give you 4 by root 2 0. Okay, 4 by root 2 and then 0. 4 by root 2 is what? 2 root 2 and then 0, right? But then we should be dividing it by sigma 1, right? Sigma 1, sigma 2. Okay, if you divide it by sigma 1 is root 2 divided by root 2 root 2, which will give you 0 minus 1. And then this, if you divide it by sigma 2 is square root of 8, which is nothing but 2 root 2. This will give you 1 0. Okay, yes. Okay, now we have here a can be written of the form y1 is this 0 minus 1, 0 minus 1, 1 0. Okay, yeah, multiplied by lambda 1. Okay, actually let's since we should be writing it in a descending order, right? The lambda values generally it should be in the descending order, right? That is lambda 1 is greater than lambda 2 is greater than lambda 3, right? But here we have lambda 1 is equal to 2 we have taken, where 2 is not greater than 8. So we'll just do the reverse, okay? We'll write y2 as y1 and y1 as y2 and then vice versa, okay? So that we can write here root 8, 0, 0, root 2 multiplied by here we need to have this x2. X2 will be equals to, sorry, x2 is 1 by root 2, 1 by root 2, 1 by root 2, 1 by root 2, and then x1 is 1 by root 2 minus 1 by root 2, right? Yeah, this is the one. Let's check which one is there. 1 0 0 minus 1 we have 1 0 0 1 minus 1 0 0 minus 1 0 1. Okay, 2 2 root 2. This is okay. According to us, it should be something like this, but then the order was like changed. Okay, here also it's minus 3, right? Okay. Okay.
Hello, sir.
Yeah, yeah.
So Q1 matrix will be 1 0 and 0 1, not minus 1.
1 0 and 0 1.
Yes, sir.
It should be 0 and minus 1, right? See, yeah, talking about Q1, right?
Yes, sir.
Q1 will contain Q1 will contain this y1 and y2, right?
Yes, sir.
Correct. So here we have here ax1 we ax1 we got it as 0 by root 2 and then minus 2 by root 2. So we got it as 0 minus 1, right? So we have here 2 minus 1 multiplied by 1 by root 2 minus 1 by root 2. Yeah. To do this, we'll get this one. Minus 1 by root 2 minus 1 by root 2. It's going to be minus 2 by root 2. It will give you minus root 2. Minus root 2, if you divide it by root 2, it will give you minus 1. Okay. So, exactly what we have over here is, okay, we have here this one, right? 1, 0, 0 minus 1, 1 by root 2, 1 by root 2. Okay, we can multiply this by minus 1, which is going to give you minus 1, 0, 0, 1. This also, here also will multiply by minus 1, 2, 2, 0, root 2. But now it's going to be minus 1 by root 2, minus 1 by root 2. Still no luck. Okay, 1 second. It is equals to 1, 0. We'll be able to easily select it, but then can someone do this?
This one, sir, I missed the question part. I'm following the solution. Which one is this, sir?
This is this activity question, second one. So yeah, there was like somewhere around here we had a static mistake, but basically yeah.
Hello, sir.
Yes.
So when we multiply a with x1, we get 2 into minus 1 minus 2 into 1. Then we get 0.
2 into 1 by root 2, 2 into minus 1 by root 2, right? We'll get 0, right?
Yes, sir. Then in second step, we multiply minus 1 into minus 1 plus minus 1 into minus 1 plus 1 into 1. Then we get 2, not minus 2.
We multiply minus 1 with 1 by root 2, right?
Yes, sir.
And we multiply 1 with minus 1 by root 2, right?
So minus is in numerator, means upper part, not in denominator part.
Minus is in the denominator, not in the upper part. I have taken it like this. Okay, I have taken it like this. See,
Yes, sir.
basically what I have done is I have taken x1 in the x1, right? This x1 here this I assumed it to be 1 and this I assumed it to be minus 1. You can do it opposite also, as you said. So if you do it like that, I take this as minus 1 by root 2 and this as 1 by root 2. Now we will get this as plus 1. Okay. And this you'll get 1, 0. Okay, which is okay then. Yeah. X2 then if you do it with x2, right? X2 will give you 2 by root 2. Okay, yeah. X2 will give you 1, 0. Okay. X2 will give you 1, 0. Then what you have is you have here 1, 0, 0, 1 you'll be getting, and then root 8, 0, 0, root 2. Then here 1 by root 2, 1 by root 2. Here it should be minus 1 by root 2 plus 1 by root 2. Okay, let's check this one. 1, 0, 0, 1, 1 by root 2. Still no. Just cross check on this, okay? So
I think so it's a computational part. We can look into it.
yeah, somewhere on the computational part I missed it.
Yes, it's a purely computational part. I think.
Okay, definitely it won't be this one because if you do it this way, right, it's going to give you -2. Okay, so third option is not correct. We could just check for this, just the multiplication. Okay, 2 root 2. This will give you 2, and then 1/√2. It's going to give you 2. Yeah, this is okay. Yeah, so let's just check this. Okay, I'll check this up and then I'll let you know. Okay. After this, we look at the practice assignment. Okay. We just look at this part of like just the SVD part. We look at it. Singular values we can be finding out. Singular values for 1, 2, 2, 1. Nothing but for A transpose A. A transpose A, you can find the eigenvalues, and then the square root of those eigenvalues are the singular values. Okay. Just solve for this. SVD decomposition. Yeah, it can be done in the same way before. Okay, this two the same. You should find the A transpose A for A transpose A or A transpose. You can find the eigenvalues and square root of those eigenvalues will be the singular values. Okay, the same thing you could be doing it here. Okay, yeah. So there are no new type of questions there. Everything just requires your computation. Okay, so that's all we have from this SVD part. Okay, if you have any other questions, you can ask.
Sir,
Yeah.
just one fundamental doubt, sir.
Huh?
The computational part is okay. I know that derivation will not come in exam also, so we can go through derivation again to got a good understanding, to get a good understanding, right?
Uh-huh.
Sir, what is the? I'm more interested in understanding the intuition and motivation behind it. What actually we mean by SVT, and what are its practical implementation, like intuition and motivation actually in short. I'm more interested in knowing the intuition and motivation behind this concept, sir.
So those intuition part, right? See, what's going to happen is
Like what actually we mean by when we say that singular value decomposition, then what we understand, and then where we can apply it. I know down the line it will be needed for some algorithm. That is one aspect, but
see this will be like really useful in this like solving and then like understanding about the matrices. Like